Today I want to characterize two connected graphs in a couple of different ways, and then we'll actually generalize these theorems in a sense as we go on. So two very easy definitions, or I guess three. So a collection of xy paths. So you have, remember, xy paths are just paths that start in x and end in y, are internally disjoint. Internally disjoint if each pair of those edges only shares the end vertices x and y, so they're otherwise disjoint from each other. Sometimes the vertices on like the interior of a path we call the interior vertices, and the end vertices are the end vertices. But so a collection of paths are internally disjoint if each pair of them only share the vertices x and y. So examples best illustrated with a picture. So you have one path from here to here, another path from here to here, and then say, one more path from here to here. That's three internally disjoint xy paths, right? X and y. They don't share vertices otherwise. But I could have a path like this, maybe this one here. This red one intersects the bottom one there, so it's not part of a family of internally disjoint paths, right? The red one's not, but those three are, okay? So simple enough. And this property will be what determines whether a graph is connected or not, k-connected or not. We did discuss that. We have a definition for k-connected, which means it's safe under the removal of k-1 vertices, but ultimately the better definition, which will be given to us by Menger's theorem, says that you're k-connected if you can find k internally disjoint paths between every two vertices. Connected is that you can find at least one. K-connected is that you can find at least k, which is a very satisfying and sensible definition for connectivity. Okay. Two other simple definitions: a cut vertex. I forget. There's an older textbook that has a funny name for this thing. Anyway. Is a vertex whose removal disconnects G. So a cut vertex in a graph G is a vertex that disconnects G. Okay, so it's a vertex. If you remove it, the graph is no longer connected. So a cut vertex is a witness for a graph not being two connected, right? If you have a cut vertex, you can't be two connected because that's a set of size 1 that disconnects it. A bridge is the same thing for edges. So a bridge is an edge whose removal disconnects G. Same definition, okay? So that's a witness for not being two edge connected. Let me just draw one graph here with cut vertices and edges. Maybe something like this. No, let's make this nicer. Oh, yeah, that's fine. Okay, so yeah, so you have cut vertices. Each of these individually, that's a cut vertex. That's a cut vertex. That is, and that is, I think that's all of them. So if you remove any one of those vertices, the graph obviously ends up with multiple components. This one, crucially, is not a cut vertex. Just again, for the complete graph example, if I remove this, it seems like it would disconnect things, but because that vertex disappears, what you're left with remains connected. Bridges, there's a bridge here, there's a bridge here. I don't think there are any other bridges in this graph here, okay? Can someone tell me, do you see a relationship between bridges and cut vertices? Like maybe something that you can state?
You'd get at least one cut vertex for one bridge.
Yes, exactly. Bridges give rise to cut vertices, not necessarily the other way around, right? Like this one in the center here, that cut vertex doesn't have anything to do with any bridges, but this bridge here gave a cut vertex, this bridge here gave a cut vertex. So bridges, I'm going to just say force a cut vertex. And Cameron, I'm going to ask you to follow up here. Except for one special case, it doesn't happen. Yeah, Ethan. I think Ethan's pantomiming there. When your graph's a single edge, then you have a bridge, but it doesn't have a cut vertex. So this is like an exception to the rule. So I don't want to write this down as like a theorem or something like that, because this is so except in the case when you have a single edge. But this is pretty degenerate. So most of the time, if you have a bridge, you also will have a cut vertex, but not vice versa. That's what I want to emphasize here. And we'll actually use this fact in the first theorem we're going to prove about two connected graphs. Okay. Okay, so theorem, I'm going to call this baby Menger's theorem. We'll prove a straight on generalization of this later, but the proof technique here is nice and gives a good warm up for this. So G is a graph on at least 3 vertices. This is essentially to avoid this scenario here, but you can deal with that separately if you want to. Is 2 connected. So again, in this context, 2 connected means that you can remove any vertex and it still is connected. You need to remove at least 2 to disconnect it. So it is 2 connected if and only if for every pair of vertices x, y, there are a pair, say, of internally disjoint XY paths. Okay, so just as I promised, you can replace 2 connectivity with the fact that you have 2 XY paths that are internally disjoint. This saying internally disjoint over and over and over again is a bit of a mouthful, but you cannot drop this property here. Saying that there are a pair or at least 2 XY paths is not strong enough. That's just not, that doesn't give you 2 connectivity. And that'll be evident in the proof here. But that's our statement there. So now when we talk about at least 2 connectivity, it's equivalent to say every pair of vertices has at least 2 paths between them. And I mean, both definitions, that what this is now the new definition in a sense, and the original definition, both are useful. It depends on what you want to do in your proof, but just like in trees, you have access to a bunch of definitions. In connectivity, you'll have access to 2 or maybe even 3 definitions, and they can be useful. This one's really nice because, again, if someone tells you the graph's 10 connected, I mean, when we generalize it, you're like, well, I've got 10 paths, so let's work with those. Let's use the properties of those to help us out. Yeah, okay. So the proof, it's an if and only if, so we'll prove both directions. I'll start off just by proving the contrapositive of the reverse direction. So if G is not 2 connected, then, well, one of 2 things happens. If it's not 2 connected, it's either simply not connected at all, or it's only 1 connected, right? That's the only alternatives there. Then G, and let me just for this first time flesh it out, either not connected, or it's 1 connected only. And actually, I don't even care about these 2 things. What 1 connected here will imply is that there exists a cut vertex, right? It's not safe. 1 connected. Duranda, is there something you can't read? I can. I like having the cameras on. I can't hear you, but because this is 1 connected. What's written here? I'm just guessing. So it's not either not connected or it's 1 connected. So it has a cut vertex. The not connected case immediately proves the theorem. What I'm trying to show is that if and only if, so I'm trying to show there's not a pair. There's not 2 internally disjoint paths. Well, if it's not connected, there's no path at all between some x and y, right? I mean, if it's not connected, there exists x and y without a path. So that would prove the theorem. The more interesting case is if it's 1 connected, then there exists a cut vertex, call it z, okay? And now let x and y be vertices in different components of G minus z. Let me scroll down a little bit here. Okay. Because it's not 2 connected, there exists a cut vertex. If I remove a cut vertex, the graph is no longer connected. So G minus z looks as follows. Here's a component. Here's a component. Here's z that was removed. There might be other components as well, but after removing z, I get multiple components. Now, since there's more than 1 component, because it's disconnected, I can find a component with vertex x and a component with vertex y. What actual property stated in the theorem am I technically using at this point here? There were two things. It's connected, but what was the? Yeah, exactly, Eric. There's at least 3 vertices. Without that, I can't get a separate x and y after removing z. There might only be one vertex. So I did actually use that there's at least 3 vertices at this point here. Okay. So now let's think about the xy paths. So every xy path that exists in this graph has to travel through z here, right? This is a component. So, I mean, the components themselves are connected. So there's stuff inside of here and there's stuff inside of here, but there's no way to get from here to here without crossing through z, because otherwise these two pieces would be the same component, right? They have to travel through this cut vertex. So, I mean, there absolutely could be a path like this. In fact, there could be multiple paths like this, right? And then you hit there and then travel around here and then get there. But each of the paths have to use v, okay? So every xy path in the original graph G uses vertex z. But that means that you can't have a collection of internally disjoint paths because they all have to share this vertex. So let me add this in red here. This path up here was impossible, right? That's not allowed because z was a cut vertex. Okay, so it means if it's not 2 connected, then you can't get 2 paths. Great, so we got one direction. Now let's do the other direction. Let's suppose it's 2 connected and actually find the 2 paths. Okay, so the reverse direction, I guess the forward direction is G is 2 connected. And we want to establish, we will find them 2 paths. Okay, so if it's 2 connected, the first thing we know, so 2 connected on at least 3 vertices. So there is no cut vertex. Right? If there was a cut vertex, it'd only be 1 connected. And there's no bridge. Right? As Cameron observed before, bridges give rise to cut vertices. If there's no cut vertex, there's no bridge. And again, this is using that there's at least 3 vertices. Because formally, you could have a bridge if you just had the 2 vertices and the edge between them. Okay. Okay, so now suppose, to the contrary, that there exist 2 vertices x and y that are in the graph that don't have 2 paths between them. Okay, without 2. Okay, let me not write that internally disjoint out. Let's throw something out first. The graph is 2 connected, so it is connected. So x and y must have a path between them. Every x and y do have some path between them. Let's suppose there's an x and y that only have one, that don't have 2 internally disjoint paths between them, so they only have one. Okay, I guess I don't have a choice but to say without 2 internally disjoint paths. Okay, so they only have one. They may have multiple paths between them, but I can only find one internally disjoint path between them. Okay. So there exist an x and y, and I want to choose these x and y in a special way. So among all such pairs x, y, choose them such that, okay, so there might be multiple pairs of vertices with only one internally disjoint path between them, without 2 internally disjoint paths between them. I want to choose the x and y pair that have the shortest path among them with that property, okay? There may be another pair of vertices that has 10 paths between them and is shorter, but I want to choose the pair of vertices with only one that's of shortest length in addition, okay? So choose such that x and y have a shortest, okay, I'm going to use a different term here, are at minimum distance. Okay, I haven't defined the term distance. I don't think this has come up here. The distance between 2 vertices is the length of the shortest path between those 2 vertices. Very natural, okay? Length of shortest path. Okay, so again, among all the pairs of vertices x, y that only have one path, again, I have to be careful with my notation, my terminology. I hope it's clear. They may have multiple paths between them. They only are able to collect one that's internally disjoint. And among all those types of vertices, choose one such that that path is minimal. Okay. By the way, if they have 10 paths between them, any one of those paths is the choice. You just take the shortest among those. among all pairs of vertices. Okay. Actually, it gets even clearer when I start to work with it. But so let's say this is X and this is Y then. And here's our one path. Again, other paths exist, but if they do, they intersect this path. And this one's the shortest one among all pairs of vertices here, okay? So let's like split this into cases, I guess. I mean, case one is really simple. What if the length of this path is just one? So like XY is actually an edge. So if XY is an edge of G, then the picture looks like this. I've got X and I've got Y, and there's no other path from X to Y, period, right? Because any other path that would exist would necessarily be internally disjoint because there's no internal vertices to the path XY, okay? So this does not exist. I've never used that notation before, but yeah, anyway, that doesn't exist. So what does that actually mean about the edge XY? Can someone see what that tells us about the edge XY in the graph?
It's a bridge.
Yeah, this becomes a bridge, right? Because there's stuff over here reachable by X, and there's stuff over here reachable by Y, but there's no way to cross. Oh, wait, is that? Yeah, there's no way to cross between X and Y. Not just this path here, but if there were a path like this, there'd be some way of traveling from here to here and from traveling from here to here. And that would be a second path here. So as no other path, no other XY path, XY is a bridge. Okay, that's a contradiction, right? We already ruled out bridges a moment ago. So that means that this shortest sort of unique-ish path between X and Y does have some vertices in it. So the picture actually looks like this. Case 2, I'm going to add a vertex W here. So there's definitely a vertex, I'll call this path P. There's at least one vertex on the interior there, and W is the one just prior to Y. Okay. So case 2 is that P has at least 3 vertices. Right here was P equaled the path, the edge XY. Okay, so in this case, now let's consider, consider the sub path of P from X to W. Let me just highlight that in red here. So along XY, there's this path here, right, that reaches W. That's a sub path. That path from X to W is shorter than the path from X to Y. I mean, because it's one less edge, clearly. Okay. This is a shorter path. And because XY was the shortest among all paths that only had one internally disjoint path, it means from X to W, there are at least 2 internally disjoint paths. Otherwise, I would have chosen X and W as my shortest path. Okay. So there exists 2 internally disjoint XW paths. Okay, now here's a subtlety. Here's X, here's W, and I'm going to put Y over here. I know those 2 are joined here. The XW, it has 2 internally disjoint paths. It's not clear that this red one is one of those 2. There does exist a shorter path between them, but this doesn't mean that this is one of the 2 internally disjoint paths. There might be 2 other internally disjoint paths. It doesn't matter though. I know that 2 internally disjoint paths exist from X to W. I'm just going to ignore the red edges entirely there. They may be involved, they may not be involved. It's immaterial, but just to be careful, it's not actually that there. So here's one of them, and here's the other of them. I know that 2 exist. Okay, and now we're almost done here. What's the key observation here? Okay, so now I want to build up 2 paths from X to Y using this diagram here somehow. But this edge here looks an awful lot like a bridge, but it's not a bridge, right? Actually, more importantly, W here is not a cut vertex. Is that what yeah, okay. So as W is not a cut vertex, this is not a special property of W. The graph has no cut vertices. So as it's not a cut vertex, there exists a path, a path, yeah, let's just say path from y to, let's name this blue thing here. These two blue paths together form a cycle C. Let's just call it C for now, okay? So there exists a path from y to C other than the edge WY. Okay? I'll actually put that one in red and then we'll be done here. Let's make sure we're on the same page here. If there was no way of getting from Y over to the blue stuff here, then removing W would split off Y from what's left in the blue stuff, right? That would mean W is a cut vertex. W is not a cut vertex, so there's some way of traveling from Y to C. I don't know where in C. It might even be X. If it was X, then we'd be done immediately. But let's say it's just like right there on C. There's some way to get from there to there. And now, I hope you see two XY paths evidenced in this, literally in this picture here, right? One is, maybe I'll even use another color here, yeah. One is start from Y, travel to the cycle C, and then go to X along the part of the cycle here that doesn't involve W, right? There's definitely, no matter where I come in, I can get over here, and it doesn't use this edge here, so I'm safe. I can definitely avoid W. And then the second path is to go to W and then travel around the cycle in the opposite direction, right? This is best evidenced by a picture here. If you name the vertices of the cycle and so on, you can describe this. Actually, it's reminiscent of like the two longest paths homework exercise, right? You're kind of like concatenating sub pieces of cycles or paths. So there's your two, okay? And so I'm not going to write out further than this, but this gives two internally disjoint XY paths, which technically is a contradiction, right? We set this up as a contradictory proof. Was it actually necessary now that I'm thinking about it? Yeah, it was necessary because we wanted, in order to get this picture, we had to start with a pair of vertices that had only one and then get a shorter one with two. So this is the type of contradictory proof that I hate the most. Okay, it's the only type that I dislike, is where the contradiction is concluding the thing that you want. Like it usually suggests like, wait a minute, shouldn't we be able to do this directly then? But it's not always that simple. So it's just a little annoying, but I mean, the proof's still, perfectly fine. Okay, great. So that's the end of that proof. So now we know we can get two paths. Now, one thing you'd be thinking here is, okay, I want to prove the same theorem for K-connected graphs. I've got a graph on at least K plus 1 vertices. That's generally not that important. That's K connected. How do I find the K internally disjoint paths? Do they exist? So that's Menger's theorem, which we'll prove sometime next week. This proof in principle can be like built up to that somehow. It's a bit challenging. We'll give different proofs. There's probably 10 proofs of that theorem. We'll probably give 2 or 3. Some proofs are very, very modern and new. The original proof is quite long and challenging. You can see if you wanted to get this one to work, you might imagine that there's a lot of details to go through. There's a lot of like this thing here, this simple thing here would be immensely complicated if it wasn't just C, but it was a bunch of these like paths here. And it wouldn't be enough that this wasn't a cut vertex. You'd need like a collection of vertices like W and so on. It can be done, but they're shorter and neater and cleaner proofs that we'll talk about later. But this is the warm up. Okay, so now we've characterized two connected graphs in one way. It's two connected if you can find two internally disjoint paths between any two vertices. The second theorem I want to talk about here is another characterization, and it's something called an ear decomposition. So let me define this first, okay? So an ear decomposition, okay? So let me mention one thing here first. I don't think I've assigned them as a homework, but there's a few of the open problems and a few homeworks where it asks you to find a decomposition of a graph. And that's a well-defined term in a graph. Let me just state it in words. This will be a specific one. A decomposition of a graph is a partition of its edges into different classes, and each of those classes is a subgraph. So it's just splitting the graph into different pieces here, right? Like, I mean, maybe I will give a simple example. Say I have a complete graph here. I can decompose this into, the triangle and this star here. That's a decomposition of that graph. I've just split all the edges in a partition into this. And like these are two subgraphs, right? It's a triangle plus a star. Vertices can be repeated, but edges are not repeated. That's an edge decomposition or decomposition of the graph. We'll talk about these things a little bit more. An ear decomposition is just a special decomposition of a graph that does or doesn't exist. Okay, so an ear decomposition is a sequence of subgraphs. You don't need it to be a sequence. It's just mentally when we produce this, you think of it more as a sequence, right? Ear decomposition or decomposition is just a collection of subgraphs. If you put them in order, then you can call it a sequence, but it doesn't add anything. So P0, P1, up to PK. Let's say, yeah, whose union is the graph G itself. That's literally what it means. Well, okay, yeah, I mean, sequences of a graph whose union is G and satisfy the following two simple properties. And then I'll draw a picture and it's instantaneous what's going on here. So P0 is a cycle in the graph, and each PI, so for I equals 1 up to K, PI intersects by vertices, I mean, the previous ones, P0, P1, up to PI minus 1, in exactly its end vertices. Okay. This actually implies that this is an edge decomposition. No edges will be shared between PI and these other guys here because only the end vertices of PI are these. Oh, I should also say, PI is a path. Did I not write that down here? So each, for these, PI is a path. That's pretty important. And it intersects those guys. Let me just draw a picture because it's totally easy to figure out what's going on. So usually, often we look at an ear decomposition in the reverse way. You also see why it's called an ear decomposition. So here's P0. P1 is a path, and it intersects P0 exactly in its endpoints. So P1 looks like this. All right, there's P1. All right, it's a path, and it only hits P0 in the endpoints of P1. Here's a P2. P2 is a path, and it goes between its endpoints are in what's already been there previous. Here's P3, P4. You can even, like this vertex can be shared here. Maybe you can do something like this, P5, and so on and so forth. Okay, so that's what it is. I hope you see the term ear, right? You're pulling ears off each time. So if a graph can be produced this way, or if you can decompose it by pulling off an ear at a time, then the graph has an ear decomposition. Not all graphs have ear decompositions. That's what the theorem will be about. Okay. Is it clear what an ear decomposition is? It's pretty easy to visualize. Certainly it's easy to build. Start with cycle, start tacking on ears. And then you can give you a graph, does it have an ear decomposition? That's less clear how to check if it has one. Because like, well, you could look for a path and pull it off, but maybe you chose the wrong path to make the procedure work. So it's not clear whether or not it has one. That's the content of the next theorem here. So having an ear decomposition is equivalent to being two connected. That's the characterization. Okay. So G is two connected if and only if it has an ear decomposition. Okay. It doesn't tell you how to find it. And in fact, the proof we do will not tell us how to actually find it directly, but being two connected is the same as having an ear decomposition. Okay. So again, it's an if and only if. It's another characterization. So we have two directions to prove here. So let's start off with the fact, suppose G has an ear decomposition. And this is a proof by induction, but I'm going to be a little bit hand wavy here. So G has an ear decomposition, and I want to confirm that it's two connected. What I'm going to do that is run the procedure of building the graph up via its ear decomposition. Okay, so what does G look like? Well, G has a cycle P0, and I'm going to show, well, I mean, is this two connected? Like this would be my base case, basically, that the subgraph containing just P0 is, and then the subgraph containing P1 up to PI, each of those is two connected. Is this guy two connected? Yeah, it's a cycle. It's definitely two connected. There's no single vertex you can remove to delete it. So is, oops, that is two connected. So our base case would be satisfied. And then let's add on an ear. First, we'll just literally add on a single ear, and then we'll imagine adding on a general ear here. Is this graph still 2 connected? It seems reasonable here. I mean, there's 2 things you can check. You can either use the previous theorem and look for 2 paths between any 2 vertices, or the original definition here I think is more valuable. Is there any vertex whose removal will disconnect this graph? Certainly by examination, no, right? And I don't want to go too far beyond examination, but any vertex in P0 here won't disconnect it. These vertices on the fringe here are like maybe candidates for thinking about it as well, but like everything here is like contained in a cycle. Basically is the reason. If you want to look at 2 vertices and try and decide, I said this would be a little hand wavy. I know 2 vertices in here definitely have 2 paths between them because they did by induction. 2 vertices on here also have 2 because they're part of a single cycle there. And so I can go this way to here and this way to here. The only real question would be, what if I took 1 vertex here and 1 vertex here? Do they have 2 paths? Certainly in this picture, they do. The point is, you go here to where they intersect, and then you have 2 directions to follow. You know, you have to like consider them simultaneously. And then this guy also has a way along its path to get to here. And then you have to get from here to that vertex, and you just travel the other way around the cycle, okay? And this is the same argument in general. So suppose I already have put, you know, together P0 up to Pi minus 1, and I'm adding on a new handle, right, Pi. And I also want to check, is 2 connected? And I hope you see, with a little bit of thought here, it's the same argument here as well. Either you say, oh, there's no vertex that disconnects it in here, or if it does, if a vertex in here disconnects this thing, it means that it separates 2 vertices on Pi from each other, because it didn't separate things on originally. Well, how can a vertex here being removed separate 2 vertices on this path from each other? It can't. They have a path literally there. And so then the question, oh, it means that there's a vertex here that disconnects it. But that clearly doesn't disconnect it either, because every vertex on this path can get to every other vertex on this path by going here and then going, well, not necessarily along this, although there will be such a thing here, maybe across several other ears. But the point is, this vertex and this vertex have a path between them that doesn't involve the edges here. And so I can go here, follow this path, and then go here, and I still have a path between them, okay? So going through the details of this, I think it's actually a little easier to use the original definition of connectivity, that you can't find, that it's safe under the removal of a single vertex. There's no cut vertex to get it. But I'm going to leave it there, okay? So if you're unsatisfied, you can think about this one a little bit more, but I think visually it's pretty clear. The other direction's a little more interesting, or maybe not more interesting, just a little more detailed. So let's show that if it's 2 connected, yeah, if it's 2 connected, then it has an ear decomposition. Okay, and we'll use this maximal subgraph strategy to get this one. So say G is 2 connected, and let's let H be a maximal subgraph of G with an ear decomposition. Okay, so actually I've used this term a couple of times here. Like, what does maximal mean? Typically maximal means it has as many edges in it as it possibly can. Okay, most edges. Like a maximal subgraph is a subgraph who has some property, and I can't add an edge to it, even with adding a vertex, that'll still have that property. Okay, so it has as many edges as possible with an ear decomposition. Okay, so we've got G. H is a subgraph of it that does have an ear decomposition. Okay, so the first question is H even like well defined? Is it empty? Like, does H have any content at all? Because we want to start up a procedure here. If it's empty, then we can't do anything with it. So I'll ask this question: is H empty? Is that even possible? Well, hopefully not. But why not? Why does G definitely contain a subgraph that has an ear decomposition? What's the simplest graph that has an ear decomposition that you can think of?
Cycle.
Yeah, exactly, Ethan. A cycle, right? Yeah. Yeah, Van, exactly same thing, right? Two internally disjoint paths implies that a cycle exists. And so, yeah, so I mean, yeah, both of those are perfect answers, right? G is two connected, so every pair of vertices has this thing here. Or in other words, the graph has a cycle. Why does it have a cycle? Well, the graph's not a tree because the tree's not two connected, right? Trees have lots of cut vertices. So if it's not a tree and it's connected, it's got to have a cycle, okay? So is H empty? No, as G contains a cycle. So H is at least one of the cycles. Right? H is not empty. I don't know what the maximal one is, but G is not empty. H is not empty. Okay. So if H equals G, then we're done. I mean, that's what we're trying to prove, right? So if H equals G, we are done, right? So suppose there exists an edge that's in the symmetric difference. The point is it's in G, but not in H, right? There's a missing edge. Let's even name the edge XY, rather. There exists an edge XY that's in G minus the edges of H, okay? Right, just to go back here, if H equals G, it means that G has an ear decomposition. I mean, H was the maximal subgraph that had an ear decomposition. Oops. Okay, so we've got an edge like that, and now let's look at two pictures here, and I'll split them up here. So if both X and Y are in the vertex set of H, and let's illustrate that, okay? So here's my graph G, and then H lives inside of G. So H is a subgraph of it. I'll draw it like this. It may span all the vertices potentially. That's not important here. But so it's got some vertex set. If X and Y are in that vertex set, so there's X here and Y here, how should I draw the edge here to like, so that it matches the situation? The edge XY, which exists, is not inside of H. So I'm going to draw it like outside of here, just so it kind of makes sense there, right? That edge was not in H. But now what can you tell me? What if I add that edge? Yeah, Ethan, exactly. I can add that edge to my ear decomposition. This single edge is a path. It's outside of the graph with the ear decomposition, so I can add it here. Then we can add XY to H. And that's a contradiction, right? H was a maximal graph with an ear decomposition, and adding XY would make a bigger one that continues to have an ear decomposition, right? This clearly satisfies the property. It could be PK plus 1, right? It's a path whose its endpoints only intersect the existing thing here. Okay, so that case is not the one. So we want the other case that says, so there exists an edge. I guess I named it differently, ZW, with Z in the vertex set of H, and W not in the vertex set of H. I don't know what that symbol is. Vertex set of H. Okay. Let me draw a picture for that, and then we'll justify it a little bit further. So this is H, and then there exists a vertex in here and here with a path like that. And this is Z, and this is W. Otherwise, we're in the previous case. Okay, and this doesn't immediately give rise to this one here. You're using connectivity here, right? So what it means is that there are vertices outside of H, right? If this case one doesn't happen, then there exists vertices outside of H. The graph is connected though, so if there's a vertex out of H, there's some way of following a path that reaches H. Just take the last edge along that path. Okay, that's what gives rise to this guy here. So it felt like there's a little bit of arguing to actually get the existence of this edge, but nonetheless that edge exists. Okay, now we finally use two connectivity, right? There we just use connectivity. Let me not flip this around because I think I did. Z is not a cut vertex, right? VTX, as G is two connected. there's no cut vertices. Okay, so G minus Z still has a path from W to H. Okay, so a couple little observations here. If I remove the vertex Z from the graph, it's still connected. There, in addition to Z, there must be other vertices in H, because remember, H started out, at the very least, it was a cycle. So at the very least, H has 3 vertices in it, no matter what, okay? Now, if there was no way of getting from W to these vertices in H without going through Z, then Z would be a cut vertex. Removing Z would separate W from these vertices here. So it means the graph definitely had a way of getting from W into there, maybe by a direct edge, maybe by some long path. Who knows? I don't know how. Okay. But then, so from W to H, let's call it a path P. Right. This is P here. But now what? What do you guys see in this picture? P plus the edge ZW in the graph G is another ear that's, that can be added to H, right? I mean, just look at the drawing here. Like W is outside, and we have a path from Z to W, and then from W to some other vertex in here, okay? Does this green path go to Z? That would be problematic. Does it go to Z? No, there might exist paths from W out here to Z, but remember, the existence of this path to some other vertex here was by the fact that Z was not a cut vertex. So I literally removed Z, and then there exists a path from W to H. So it can't end up in Z because Z is not there for it to end up in. Okay, so after removing Z, I find the green path. And then I go back to the original graph and say, oh, well, P obviously existed in the original graph too, and just tack onto it the edge ZW. So that's this path here, P plus ZW. And that's an ear, right? This path here, this path plus the blue piece satisfies exactly the ear decomposition property, that it's a path that's only intersecting H, the so far ear decomposition, in its end vertices, okay? And so this is actually a contradiction as well, right? So we're only left with the case here, that they were equal, right? If they were equal, then we're done. Otherwise, we suppose there was an edge not in the two of them, and we reached a contradiction in both cases. So that's the end of the proof there, okay? So being two connected is the same as having an ear decomposition. Okay, so we're about done. Let me mention something, because we might not have time when we get to it in the other class. Next time, we're going to look at 3 connected graphs. 3 connected graphs also have a cool characterization where you can build them up from something. Like here, we now know that 2 connected graphs can be built up from a cycle and then adding on paths in some fashion. You can always build your 2 connected graph that way. Or alternatively, you can always decompose it by pulling off appropriate ears. That property is useful for applying induction to a 2 connected graph and doing all sorts of things. 3 connected graphs have a similar property. It's more complex, but it's similar. We know of no such procedure for 4 connected graphs and beyond. Like, we do know how to characterize 4 connected graphs by saying there's 4 internally disjoint paths, but we don't know how to build them up mechanically or break them down mechanically from a starting point. That I've listed as an open problem. No one knows how to do that. It's not clear it's even possible, like with a simple procedure, but it's tantalizing because it can be done with 2 and with 3. Okay. All right. So that'll do it.